So, buffering system, what are these reactions? As we said, atmosphere has trace amounts of CO2, which is constantly getting dissolved and mixed into the ocean. As the ocean is getting churned, it exchanges gases and materials with the atmosphere, as we saw. And we already saw that CO2 dissolves in water. There is dissolved CO2 and there is something called aqueous CO2, where the CO2 molecule is kind of hydrated and surrounded by water, but we won't bother with such details. So essentially the CO2 gas in the atmosphere is constantly being exchanged with the ocean. H2CO3 is getting formed. As we said, H2CO3 is constantly getting moved into bicarbonate, or CO3 minus, and H plus, which gives us a move towards decreasing pH because of acidification. But the HCO3 minus is further splitting into carbonate, or CO3 2 minus, and releasing another H plus, right? So what is critical here? Critical is how fast CO2 is being added to the system. If it is equilibrated at some natural level because of the natural winds, natural rainfall, natural ocean river exchanges, and so on and so forth, and the CO2 in the atmosphere is not increasing very rapidly, then the ocean is nicely buffered, it's maintaining its pH at 8.1 and so on. But if you change the rates, or if you have processes which are taking out the carbonate and bicarbonate ions from the system, how can that happen? Basically, you have calcium that's being brought in constantly from the rivers, all the weathering of rocks and organic matter from the forests and wherever the water is coming from into the rivers and into the ocean, is bringing in lots of calcium. Calcium has two positive ions. It's going to satisfy its polarity by combining with CO3 carbonate, which has two negative charges, and it's going to form calcium carbonate. Calcium carbonate tends to be either dissolved, or it's associated with the coral, zooplankton, and so on, which can sink, right? So that precipitation of calcium carbonate into the deeper ocean can take out HCO3 from the system and leave H plus, as you can see here. How much of the calcium carbonate actually reaches to the bottom obviously depends on how acidic the waters are. Remember the CO2 profile, we said it's low near the surface, increases to about 1 kilometer and then decreases, but at depths temperatures are colder, pressure is higher, water is still acidic even though CO2 is decreasing. So calcium carbonate is constantly dissolving, but if it reaches a certain depth called the lysocline, or calcium carbonate compensation depth, CCD, then it can escape, because that's the depth where the amount of calcium carbonate coming in and the amount dissolving are equal to each other. That's kind of the equilibrium point. Below that, less calcium carbonate is dissolving than dropping out. So tiny amounts of calcium carbonate make to the bottom of the ocean with this process, and obviously over time, because there are worms that are creating turbidity in the sediments, or the volcanic activity, or oceanic crust formation, and so on and so forth, are constantly happening at the bottom of the ocean. And so there is some dissolution of this calcium carbonate is happening as well, which is releasing the calcium and carbonate ions back into the system, which are combining with this H plus ion that's always available, and producing bicarbonate again. So the equations below, H2CO3 going to carbonate and H plus, dropping the pH, whereas HCO3 minus, or bicarbonate, can combine with H plus and reform carbonic acid, and pH increases, or you go towards alkalinity, right? So looks complicated, but just stare at it for a little bit. There are just 2-3 equations which are very critical for understanding a lot about ocean's role in global warming and ocean's role in important life forms like corals and calcium carbonate forming shells and so on and so forth. Right? Ocean has played a large role in regulating climate directly by the heat budget, but also because of this ability to keep carbon dioxide buffered inside its system. Okay, so this is something we must pay attention to. So we'll continue this again a little bit further. Very important concept, so watch it as many times as you need to and make sure you understand it.